Hi, in this video I'm going to show you how to prepare a buffer solution. So let's say we have a problem that says, describe how you would prepare a phosphate buffer with a pH of 7.40. Now, phosphate ion is PO4 3-, and there can be three different equations that involves PO4. We can have H3PO4 plus H2O forming H3O plus H2PO4 minus. We can have H2PO4 minus plus H2O forming H3O plus HPO4 2 minus. And finally, we can have HPO4 2 minus plus H2O forming H3O plus PO4 3 minus. And how do we know which one to use? That is when we're going to look at the Kas. So if Ka1, Ka2, Ka3. Ka1 we're given as 7.5 times 10 to the negative third. Ka2 we're given as 6.2 times 10 to the negative eighth. And Ka3 we're given as 4.8 times 10 to the negative 13th. Now to know which one we have to use, we're going to have to use pKa, which is negative log of all the Kas. So let's quickly find the pKa1, pKa2, and pKa3. So pKa, negative log of 7.5 e to the negative third is 2.12. pKa2, negative log of 6.2 e to the negative eighth is 7.2. 7.21. pKa3, which is negative log of 4.8 e to the negative 13th. So this is a 1 over here, e to the negative 13th. Is going to be 12.3. 12.32. Now, which one do you use? We're going to look at our pKa's. We're going to use the one that is closest to our pH. Our pH is 7.4, so the pKa that is closest to 7.4 is pKa2. So this is the equation that we're going to be using. Now that we know which equation to use, we're going to use the Henderson-Hasselbalch equation, and that is, let me write it over here, Henderson and this one says pH is equal to pKa plus the log of the concentration of A minus divided by the concentration of HA. So basically the concentration of the conjugate base divided by the acid, or base divided by acid. Base divided by acid. It can be log of A minus divided by HA, or the log of base over acid. Now in this case, let's see, what is the conjugate base for the acid? Our acid is H2PO4. This is our acid. What is our conjugate base of it? Is HPO4. So we're going to have pH is equal to pKa plus the log of the conjugate base, which is HPO4 2 minus, divided by the HA, the original acid, which is H2PO4 minus. And now we're given with the pKa. We found the pKa, and we found we're given with the pH. So 7.4, which is the pH in the given buffer solution, equals 7.21, which is our pKa2. Is plus log of HPO4 2 minus divided by H2PO4 minus. I'm not given the concentration of these, so we're going to have to solve for that. So 7.40 minus 7.21 is 0.19. 0.19, I'm going to write on the side. 0.19 is equal to log base of 10 times HPO4 divided by H2PO4 minus. Now that we're here, 10 times 0.19 power is going to be, if we take the 10 to the 0.19 power, we're going to separate this by itself. So 10 to the 0.19 power is equal to the concentration of HPO4 2 minus divided by the concentration of H2PO4 minus. So 10 to the 0.19 power is going to be 1.55. That is going to be equal to the concentration of HPO4 2 minus divided by the concentration of H2PO4 minus. So what does that tell us? That tells us the ratio of our conjugate base divided by our acid is 1.55. So what this tells us is we need to dissolve 1.5 moles of HPO4 2 minus and 1.0 moles of H2PO4 minus in enough water to make up a 1 liter solution of, let's see, what's the pH? Of a pH of 7.4. Okay, now let's quickly look at another example and use our HH equation to see how we prepare. All right. So the question asks, how would you prepare 1 liter of carbonate buffer at 1.10 pH? So we're looking for a carbonate buffer. Carbonate is carbonate ion is CO3 2 minus, and we ask the pH is 10.10. That is our pH and that is our ion. So this one can form two equations. We can have H2PO4. H2PO4. No, sorry, not PO4. Now with this ion, we can form two equations. We can have H2CO3 plus H2O, which forms HCO3 minus plus H3O plus. And we can have HCO3 minus plus H2O to form CO2 minus. CO3 2 minus, sorry. CO3 2 minus plus H3O plus. Now we're going to use K1 and Ka2. If this is basic, then you'll be using the opposite, Kb, and still going to find which one is closest to the pOH. So in this case, K1 we're given as 4.3 times 10 to the negative 7th. K2 we're given as 4.7 times 10 to the negative 10th. Now the pKa is going to be negative log of 4.3 e to the negative 7th, which is 6.37, and the pK of negative log of 4.7 e to the negative 10th is sorry, this should be 11th, negative 11th. So to the power of negative 11th is going to be 10.33. Now, which one is closer to the pH of 10.2? Which pKa is closer to 10.10? Now the pH that is the pKa that is closest to 10.10 is going to be 10.33. So this is the equation that we're going to be using. Now that we know the equation that we're going to be using, we can plug in our numbers into our HH equation. So pH plus pKa is equal pH is equal to pKa plus log of conjugate base divided by the original acid. So what is the conjugate base? Conjugate base in this case is CO3 2 minus. So 10.10 pH is equal to pKa, which is 10.33, plus the log of concentration of CO3 2 minus divided by the concentration of HCO3 minus. Now if we do 10.10 divided by minus 10.33, we're going to have negative 0.23 is equal to log of CO3 2 minus divided by HCO3 minus. So if we use 10 to the negative 0.23's power, that would be equal to 10 to the negative 0.23 power. That's going to be 0.59. And what is the ratio of? The ratio is to the conjugate base divided by the acid. So now we can have our explanation to what we need to prepare. So we need a mole ratio of 0.59, and this is CO3 2 minus compared to HCO3 minus. And the ratio is 0.59 to 1.0. And dissolve it in enough water to make up a 1.0 liter solution of 10.10 pH. And that is how we prepare this buffer solution. Thank you for watching.